Here says we have hemoglobin, which is a huge molecule. It has 2,952 carbon atoms sharing electrons with one another, and with 4,664 hydrogen atoms and 812 nitrogen atoms, as well as 832 oxygen atoms, 8 sulfurs, and 4 irons. That's the molecule with its huge size, with all those atoms, that positions an iron atom just in the right place to bond oxygen, to form a nice ion instantaneous dipole attraction with oxygen, which then carries the oxygen through your blood. So it's not super strong attraction, so that when it reaches its destination, it can then release the oxygen. But that is the molecule, that's one of the molecules in your blood that carries oxygen. So we want to calculate its molar mass. So we need to multiply the masses on the periodic table times the number of atoms we have of that element. So 12.01 for carbon times 2,952. So that gives me 3.545 times 10 to the fourth. I'm going to add to that the mass from the hydrogen, 1.008 times 4,664. So that's 4.701 times 10 to the third. And then I'll do the nitrogen, 812 times 14.01 gives me 1.14. 4 sig figs. 1.138 times 10 to the fourth. For the oxygen, 832 times 16.00. 1.331 times 10 to the fourth. 8 sulfurs, so 8 times 32.066. 256. 4 irons, 4 times 55.845. 223. So if I add that all up, I get 65,320, or 6.532 times 10 to the fourth. So that could be an AMUs per molecule, but really that would be the molecular mass, right? That's the mass of a molecule, or molecular. If I want the molar mass, it's the same number, but it's in grams per mole. Or if I had a mole of hemoglobin molecules, it'd be over 65,000 grams. So that's the molar mass. Then it says an average adult has about 5 liters of blood. Every milliliter of blood has approximately 5 erythrocytes, or red blood cells. And every red blood cell has about 2.8 times 10 to the 8th hemoglobin molecules. 280 million hemoglobin molecules. Then calculate the mass of molecules in grams for the average adult. So basically it gives us a bunch of relationships and then asks us to do a conversion. So the relationships it gives us, we'll just write those down. So we have the molar mass. That's a relationship. That's the number of grams per mole. Then it says an average adult has 5 liters of blood. So one adult equals 5 liters of blood. Then it says every milliliter of blood has 5.0 times 10 to the 9th cells. So 1 milliliter of blood equals 5.0 times 10 to the 9th cells, blood cells. And every blood cell has 2.8 times 10 to the 8th hemoglobin molecules. So 1 cell equals 2.8 times 10 to the 8th molecules of hemoglobin. Then we want to calculate the mass in grams of hemoglobin in an average adult. So we want to take the unit 1 adult and convert that to how many grams of hemoglobin are there. So we use a relationship between adults and blood to convert the adults to blood. Then we'll know how many, the relationship between, well, we'll have to go liters to milliliters, so we'll need that. We get that from the metric table. So we can go liters of blood to milliliters of blood. Then we'll go from milliliters of blood to cells, then from cells to hemoglobin molecules. Then how do we get to grams of hemoglobin? Well, we have a relationship between grams of hemoglobin and moles, so we'll need one more relationship to bridge the gap between molecules and moles. And what's that relationship? Right, Avogadro's number. So we'll need 6.022 times 10 to the 23rd molecules of hemoglobin per mole. So I'm going to need space here probably to fit all this in. So let's go for it. 1 adult equals 5.0 liters of blood. One liter is 10 to the 3rd milliliters. 1 milliliter of blood equals 5.0 times 10 to the 9th blood cells. 1 blood cell has 2.8 times 10 to the 8th hemoglobin molecules. Avogadro's number of molecules equals 1 mole. And the molar mass tells me that every 1 mole equals 6.532 times 10 to the 4th grams of the hemoglobin molecules. So everything cancels. Liters, liters, milliliters, milliliters blood, cells, cells, molecules, molecules, moles, moles. I've got the unit I want. So then I just have to plug it in. So I do 5, multiply the numbers on top, times E3, times 5.0 E9, times 2.8 E8, divided by 6.022 E23, times 6.53 E4. That gives me 759. Really, I need to limit that to 2 sig figs because of some of the numbers I'm plugging in are limited to 2. So it should be really 7.6 times 10 to the 2nd grams of hemoglobin in the average adult. So this is, I mean, the unit conversion method is so useful. It's useful in your daily life. If you want to know how much of something you need or how much of something you have, but you don't have it expressed in the right units, and you know a bunch of relationships, or you can Google a bunch of relationships, you can solve almost any problem using this method. Yes? Yeah, Avogadro's number is just a number that's equal to a mole. So just like the number 12 is the same as saying the word dozen, saying the word mole is the same as saying Avogadro's number. So you could have a mole of anything. If you have a mole of atoms, that's Avogadro's number of atoms. If you have a mole of molecules, that's Avogadro's number of molecules. So whatever you're working with, if you have a mole of those things, you have Avogadro's number of those things.